our seats, please. It's on the screen. Let's take our seats, please. At 2 p.m. they remove empty chairs from the room, so if you want a chair, please be seated. With the three gentlemen at the front, please be seated.
People in the panel, please come up. Leisha and George. Where'd George go? Okay, welcome to the first panel discussion of the Cosmic Controversies meeting. And our panel is charged with a discussion of the resolution of the H-naught discrepancy. And for those of you who were here for the parallel session this morning, we resolved it. We're good.
Coffee break.
But nonetheless, we have a panel to discuss where we are. And Adam Reese, George Estathiou, and Leisha Verdi. And Adam will discuss the local measurements of the Hubble constant, and George Estathiou will discuss the CMB results and where we are with respect to the early universe, late universe Hubble constant measurements. And Leisha is our resident theorist who will tell us how to explain everything. So this was the panel, the session this morning, and the invitation that was sent out to the panelists said, the H-naught panels on the first day, the goal of which is to have a lively discussion, broadly framing the controversy, engaging the audience, and I think it also had something about surprising the audience. The discussion will be informed by a morning parallel session on H-naught, which we've done, and there were the speakers and also the contributed talks. The issues that we're facing, of course, is the H-naught tension real? Have the systematics, if we're going to resolve this, have the systematics been retired to the level that we can answer that question? What would be required to establish unambiguously if the tension is real or not, and what is promising for the future? So I hope those issues will come out in both the contributed panel parts of the discussion. We will, after the panelists speak for approximately 20 minutes each, we will have conversation amongst the panelists, and then we're going to open it up to audience participation. So I hope you'll have a lot of opportunity for discussion. Let me just say a few words about history to set context of the panel. We're all familiar with the fact that the Hubble constant has had a long history, beginning with Hubble's measurements of distances and even earlier publications of values of the Hubble constant by Lemaitre and Robertson. Hubble had a value of about 500 kilometers per second per megaparsec, and we heard this morning that that's tension, that's right. What's this? It's a mild headache in comparison. Bada resolved the red giants in M32 and other local group galaxies, as we heard this morning. And ultimately, the Hubble constant settled at a value between about 50 and 100, stayed there for over a couple of decades, and there was no agreement, and that was resolved at the 10% level in 2001. Now, the current tension in H-naught has largely been defined by measurements of Cepheids and also by the CMB. And I'm just showing here, again, as a function of time, the Hubble constant measurements. The key project results in 2001. We got a value of 72 at that point with an uncertainty of 10%. And as a function of time, the value of the Hubble constant locally hasn't changed all that much. What has shrunk are the uncertainties. And you can see most of the points up there come from the Shoes group and Adam and his collaboration, and also the Carnegie Hubble program. And the CMB result, shown in black here, started out also in the low 70s with the WMAP observations, and recently those values have been decreasing. The Planck 2018 results are shown at the end there, and those are getting a value of about 67.4. Here's where the gravitational wave results lie at the current time, right in the middle. But if we take at face value the difference between Shoes and Planck, it's somewhere in excess of 4.4 sigma, maybe as high as over 5 sigma. I think we'll hear later in the panel. Here's a different version of recent H0 values. These are published values now in the literature, recent measurements. The Cepheids shown in blue there are 19 Cepheid calibrators. For the tip of the red giant branch shown in red, there are 18 calibrators, and these both calibrate the type 1A distance scale. There are 6 lenses shown in purple there. The Planck results are in black. And DES plus baryon acoustic oscillations, Big Bang nucleosynthesis are at the lower end, and the gravitational waves are that flat line at the bottom. And we hope, as we heard this morning, that the numbers will increase soon. I think Adam would like us to include Miras. At the moment, there's one galaxy that has a distance with Miras and type 1A supernovae. Systematic errors, of course, are the name of the game. We all understand how to measure statistical errors. They're well defined. Systematics are the challenge, and I think in astrophysics, not as clearly defined as they are, say, in physics or other sciences. We worry that is what I mean by 5 sigma the same as what you would mean by 5 sigma, and that definition, there's no precise definition for that. I'm hoping that during the panel discussion, we'll hear about what future measurements that could rule in or out the need for new physics. We heard from Joe Dunkley this morning, a very nice talk about how polarization measurements are going to help. So upcoming ground-based observations, experiments for the CMB should be very useful in this regard. In terms of local determination of H0, addressing systematics is going to be the key, always has been the key, and there are issues for all the different kinds of ways that distances can be measured that I think until those are resolved and we understand the reason for the differences, we're going to argue about this for a while. What's the current state of theory and what are future tests for new physics? And so I'm going to turn that over now to the panel, and Adam, you're up.
Oh my God. I didn't realize we were choosing teams, so I'm right. I'm on team science. All right, the expansion of the universe. So we had a lovely meeting this morning, but I recognize that many people were over on the other side of the room. So let me just very briefly remind you of what the situation is. So we have a wonderful standard model of... What? Microphone. Sure. So you want me to use the wireless? Is this on? All right, is this better? Yeah. Okay, so we have a wonderful model of standard cosmology, vanilla lambda CDM, with 6 free parameters, a number of ansatz dominated by dark components whose physics we don't totally understand, but that's okay. We make simplistic assumptions about them, and then we use the cosmological model as it would have looked before recombination, so this version over here, to predict the size of physical fluctuations in the early universe. We can also use it to predict the baryon density. We then compare those predictions to the angular fluctuations as we see in the CMB, or alternatively, we may measure the baryon density, and in that step, we essentially calibrate the 6 free parameters of lambda CDM. We then use the calibrated form of the model, and it evolves into looking like a very different model, like you see there, over 13 billion years. We use that to predict the expansion history of the universe. Now, there are some checks along the way. Baryon acoustic oscillations, high redshift supernovae. I like to think of them as guardrails. They don't tell you if you're on the right road, but they keep you from going off of curves in the road, and like acceleration. And then finally, we get this beautiful prediction of the Hubble constant, 67.4 plus or minus 0.5. And so the ultimate end-to-end test of the universe and this entire story is to try to measure locally in the late universe the value of the Hubble constant to comparable precision. So let me just now talk you through the basic concepts of a distance ladder, and this is a little predicated on the shoes ladder, but there's two very important concepts: co-location and consistency. Co-location is that two objects may be located in the same place, so one can calibrate the other. And consistency is that you see those objects somewhere else further out in the universe and recognize them to be the same objects, and hopefully you measure them consistently as well. And so we use geometry to calibrate Cepheids at kiloparsecs or megaparsecs, in galaxies that are 10 to 40 megaparsecs away, where supernovae and Cepheids are co-located. We may calibrate them, and then finally, of course, out into the Hubble flow, where supernovae are calibrated, and of course the redshifts belong to the supernovae as well. We measure the expansion rate of the universe. Now, a couple of notes: if you look at the nutrition facts on your distance ladder, you will see that there is 0% astrophysical modeling. Barry talked about a lot of potential modeling, but that's not the way people do distance ladders. It's all empirical. There's less than 1% general relativity. I would say less than 1% lambda CDM, and it's only 73 calories. The warning, of course, is that you have to measure objects in the same way, and they need to be the same objects across the ladder, and so we'll get into that a little bit. So this is the current state of the art for the shoes team, 73.5 plus or minus 1.4. That's a total uncertainty of 1.9%, and if your short-term memory works at all, you will recognize that is very different than the Planck prediction by about 4.2 sigma. Our goal is to try to measure a 1% measure of the Hubble constant. That would be 0.02 of a magnitude as a threshold for errors. The current tension is more like 0.2 of a magnitude, 10 times bigger, and that's very big. I think many of us would have to give back their PhDs to get errors that big, at least in measurement space. So this is a very large amount. So let me walk you very briefly through. Step one in a distance ladder, you use geometry to calibrate some kind of standard candle, and of course it's very critical to measure those objects, in this case Cepheids, consistently. And so we have used 5 different independent sources of calibration, 3, all good to better than 3%. 3 of those are different flavors of Milky Way parallaxes, and having worked on parallaxes, I can tell you they're all very different. They have different systematics. So HST fine-grained sensor, our own from spatial scanning, and Gaia DR2. The Large Magellanic Cloud detached eclipsing binary systems measured by the Arakaria group have really matured. They're good to about 1.2%, and the masers in NGC 4258. Now, we've realized a lot of improvement just in the last few years by being able to measure the Cepheids in the anchors and in the supernova hosts with the same instrument, the same filters. And part of that was to calibrate the linearity of that single instrument system over a factor of 1,000,000 in flux, so that now contributes 0.3% in the Hubble constant. So that's something to think about. You really need linear measurements. And we make every effort to measure Cepheids over a similar range of metallicity and period, so that we don't have a lever arm to systematics. So it's interesting to break out the value of the Hubble constant you get from each of these individual anchors taken separately. And there's a little bit of range, but you can see there's no way to avoid or get out of our problem just by choosing your favorite anchor. These all agree to about the 2 sigma level or better, and are giving us a fairly consistent picture. Now, let me move on to step 2. This is where we observe Cepheids in the hosts of type 1a supernovae. This, sadly, is the rate-limiting step for measuring the Hubble constant, its precision. The precision goes as how good one supernova is, which is about 6% over root n. And nature is only producing so many type 1a supernovae in the volume to which we can reach supernovae with Cepheids. And so as of this year, 2019, we are putting together the complete sample. This is every type 1a supernova that is in range of Cepheids. It needs to be a good, well-observed type 1a supernova, and the host has to be a late type host within about a redshift of 0.01. And these are really all of them. We used to be quite limited in finding supernovae, but I think since about 1995, maybe 2000, we're pretty complete. So there's only about 1.5 per year. So we will double the sample this year from 19 to 38. And even if Hubble lasts a long time, I don't think it's possible to double this sample again. So this is sort of the end of the road. And most of these supernovae were measured with the same surveys as the ones in the Hubble flow. Dan did a very nice job early this morning talking about the Hubble diagram of type 1a supernovae. It's important to note that we don't measure too close because we want to avoid coherent flows, bubbles, local voids, things like that. We don't want to measure too high a redshift because of the potential for changes in the expansion rate of the universe. There's kind of a sweet spot between around redshift 0.02 and 0.15 where most of these are measured, and there's plenty of supernovae there. This is not the rate limiting step. Okay, so in terms of systematics, one of the reasons that we found our results pretty firm is that we've paid a lot of attention to systematics, particularly in the analysis. So although it's 0.2 of a magnitude, that's just statistics. In terms of systematics, there are many things we have varied in the analysis. We have varied the reddening law. We have varied how you treat the Cepheids, how you do outlier rejection. We have varied whether you assume there's a metallicity gradient in galaxies and you regress that out as a separate variable. We varied the period luminosity relationship. Is it one slope? Is it two slopes? Does it have a break? We varied the supernova light curve fitter we've used, the types of host galaxies that we allow supernovae in. And you can see there's a small range there, but this is not, again, any way to get out of this problem. And we propagate the variation here in our final uncertainty. So over the last 15 years or so, the uncertainties have been coming down. We paid close attention to the largest sources of error and have devised experiments to attack these. And in the last 3 years, most of the progress has been on the anchor side, on that first step, Milky Way parallaxes and fluxes, and the other things listed there, as well as the count rate nonlinearity. What you can look forward to in the next 2 years is this doubling of the sample, and hopefully Gaia DR3. Every time Gaia gets a release, we hope that we'll get even better parallaxes. Okay, so let me make a few general comments now before moving into some comparisons. So why Cepheids? Well, they have the longest distance range, and so if we're limited by the number of supernovae, they're very valuable. There are the most opportunities to anchor them. You can observe them individually in galaxies, so even if the galaxy is very big, you can pick them out. We can measure their photometry consistently between the distant galaxies and nearby. But one of the things I really want to make clear here is that they are the most tested. Dan showed this briefly. These are all the measurements in the last 20 years using Cepheids and supernovae to measure the Hubble constant. And this is a wide range of different teams, different instruments on HST measured at different wavelengths, different people doing the photometry. Our esteemed chair measured the point in the middle there, 74.3 plus or minus 2.2, as the final recalibration of the HST key project. That's very consistent, even a little higher than where we are. And George there measured the point 72.5 plus or minus 2.2. So lots of eyeballs, lots of people, lots of instruments, lots of different ways of doing this, fairly consistent results. Okay, so a couple of months ago at KITP, 6 different groups presented new results on the Hubble constant, all things over the last couple of months. And there's a nice review by Licha Verde and others in Nature, and myself, in Nature Astronomy. The worst thing you could do is just take a simple average of this because there's a lot of covariance here. But because There is category 1, which I call supernova distance ladders. These all have correlation because they use some of the same supernova samples. However, I just indicate within each of these are different ways of calibrating the supernovae, and then the different lines are different calibrations, different anchors that you use to calibrate the luminosity of the Cepheids. Here are Miras, which are an alternative to Cepheids or TRGB. Here's TRGB. The difference you see here are different ways of estimating the extinction to the Large Magellanic Cloud for TRGB, and we can talk about that later. Here is Holy Cow, and then SBF, distance ladders, single rung method. So how do you get an independent combination when you have things correlated like this? Well, it's like ordering at a prefix menu at a restaurant, right? You get to order one thing from category 1. That's like your meat course, okay, or vegetarian course if that's what you prefer. You get one from category 2, right? That's light plates or something like that. That's independent of 1. Then you get category 3, that's like dessert. You automatically get dessert, which is great. And category 4 is maybe the cheese plate. So you can choose one from each of these, make your own choices, and then you get one peremptory challenge. There's always something that people don't like. You know, at a restaurant, maybe it's the broccoli, maybe here you don't like lensing or something, I don't know. So we have formed all the combinations that you can from category 1, 2, 3, 4, and a peremptory challenge. And here they are, okay? So here is using Cepheids to calibrate the supernova distance ladder, or Miras. I give you 3 options for TRGB, and then there are peremptory challenges here as well. No type 1a supernovae whatsoever, no lensing whatsoever, no use of the LMC of the Milky Way or NGC 4258 individually to calibrate any distance ladders, no use of SBF. Okay, so these are different combinations, which could be the combination you would choose if this were you ordering at the restaurant, okay? Now, you could play the same game in the early universe. You can choose Planck, of course, it's the most precision, and in a way, that's a peremptory challenge, no BAO. There's Planck TT, then there is no CMB. So if you're uncomfortable with the CMB, there's BAO calibrated by BBN. And then, if you like the CMB, but you just don't like Planck, no offense to George, then you get 3 choices of CMB experiments to calibrate BAO: WMAP, ACT, and SPT. And what you see is a very consistent picture. This is really the essence of the tension that we've been seeing. But we can go a little further with this, take these combinations and take these combinations, and of course, the next thing you want to do is make a matrix out of these, right? So here are all the late universe orderings from the menu on this axis, and I've ordered them in terms of precision. So the most precise on the left, and here's all the early universe. The most precise is on the top. And the difference in the Hubble constant is what is shown in these individual squares. And the first thing you want to look at is it the high precision things over here that are driving the difference? And what you see is, no, not really. It's pretty flat. It's not the highest precision. It's pretty flat across here. And then we move on to the tension matrix, which is going to be the 4th Matrix movie. Is going to be called the tension matrix. I think that's a good title. Here is the tension matrix. And if we zoom in here on Planck, and I think that's fair because Planck is the most precise and it is consistent with all the early universe things, then you see what we saw at Santa Barbara, which is, depending on what you choose to believe, the range here is anywhere from about 4.1 to 6 sigma. And you could break that out in terms of the different ways of calibrating the late universe measurements. So Cepheids can give you anywhere from 5 to 6 sigma. TRGB, depending on the way you calibrate the LMC extinction, 4.1 to 4.8 sigma. If you don't like lensing at all, you're at about 5 sigma. If you don't like to have to choose between TRGB and Cepheids, there's Miras, 4.8 sigma, or if you just don't like supernovae, I don't know who that would be 4.4 sigma. So this to me is probably the simplest statement. No choices have been made, you know, pick your favorite method, pick your favorite version, but this is sort of what I see as the thing that is hard to escape at this point. So we heard a little bit about new physics. My own opinion, as Isaac Newton said, I fate no hypothesis. I really do not know what is going on. I really like this recent paper, the Hubble Hunter's Guide, did a very nice job of laying out the possibilities. I think one of the most exciting things is if you do shift the sound horizon, some papers claim a better fit to the CMB, which I take to mean maybe it's not worse. But most excitingly is that it predicts new features in the CMB, and so that's something one could actually go look for. Okay, so last things I want to say. I hear this often, somebody mentioned it as the Eddington hypothesis, that you cannot believe a measurement until you have a theory. And I have to say I disagree with that. I think we can have measurements without explanation, and they linger for a long time sometimes. The precession of Mercury, the solar neutrino problem, missing baryons, and things that are still with us, the lithium problem, the CMB cold spot, the flat rotation curves, where is that dark matter, the accelerating universe, or why is lambda so small? These problems are great. These problems are the seed corn. These problems are the seed corn of our field. We should not dismiss them just because we don't understand them at present. They are often our key clues. And as I said, don't shoot the messenger if you don't like the results. We have to just follow the evidence. So, final thoughts are the discrepancy. It's around 5 sigma, it might be 4 sigma, it might be 6 sigma. It depends on what combination of things you choose, and I think we will see this situation evolving over time. It is just a simple statement. Nobody is measuring anything in the late universe that is lower than what we expect the expansion to be from the CMB. That is a very powerful statement. It is very hard to converge on 67 if everybody is measuring above that. I'm not a mathematician, but I think that statement is true. It's robust in that it would require multiple catastrophic failures. There are multiple things giving us this picture. It is not, I keep hearing people talking about shoes versus Planck, and it's not that at all. I hope I made that clear from this broad set of things that I showed. I think it's very interesting. To people who don't think it's interesting, I think your Bayesian prior on lambda CDM must be higher than 5 sigma. And then you can overcome that. I understand that. But again, this gets back to my previous point. We can judge a measurement without understanding why that is. As I said, I feign no hypothesis. I think we have to keep following the evidence wherever it goes. The universe might be more clever than we are now. I know that there are very clever people in this room, so I don't mean to insult anybody, but there may be a better idea that comes along later, or the universe might have a better idea that we just don't have now. But finally, what I really want to say at the end is, really, no matter how this turns out, everyone will remember they were right. So that's the takeaway. And I'm happy to switch over to the next person now. So I think I'm going to cue up George's talk now. This machine.
Thanks, Adam. So I must say, I'm unusually nervous about this. Okay? So I want to start by saying that I've got tremendous respect for Adam and Wendy and other people that are working on this very, very difficult problem. But I have a slightly different perspective, and the reason I'm nervous is because I was a graduate student in the 1970s, and I was scarred by the H0 debate. This is the vocalers, who, as Simon said this morning, was arguing that H0 was 100, and Sandage, who was arguing that H0 was 50, and meeting after meeting, they would get up, give talks, presenting their particular points of view, and there was no real sort of discussion between them, or contact between them, and it left me as a graduate student completely clueless about what was going on with the distance scale. So I don't want this presentation to look as though it's H0 measurement versus Planck or CMB battle. Okay. As Adam said, the universe is cleverer than us. I don't know what the solution is, but I have a different perspective, and I'll give that for what it's worth. So, what I wanted to do is to look at this problem in 2 parts. One is on the CMB, and then the other one is on the distance scale measurements themselves. And my contribution really is primarily on the CMB side of it. So here's the Planck power spectrum. And this is almost identical to the one that appeared in the 2018 Planck papers. And since then, one of the things that I wanted to do was to push the data, Planck data, much harder and see what happens, because various people have pointed out that there are little oscillations and discrepancies like A lens and so on and so on. What happens if we push the Planck data harder? Okay, and that's the 6-parameter lambda CDM model, basic lambda CDM plotting there. And so we've done this with Steve Graham, and you don't have to do any statistical analysis to see what happens. Push the Planck data harder, that power spectrum changes to that. And you can see that it locks on even more accurately to the basic lambda CDM solution with parameters unchanged from the 2018 papers. So our conclusion from very long analysis is that the lambda CDM fits the data beautifully. So is there a possibility that the Hubble constant from the CMB is wrong? Then, assuming this underlying cosmology, then I think the answer is no. There's this beautiful comparison here between, so that's H at Z versus angular diameter distance, basically measured from BOSS DR12. Those are the contours. So 3 redshifts. And then the Planck results, the CMB constraints, sit on a line-like degeneracy. Okay? This is a beautiful plot, because if you see the line-like degeneracy, that spread, the spread is dependent on the accuracy with which Planck can determine omega matter H squared, which I've labeled little omega matter there. Okay, so if you do the same with W map, for example, you'll get a line-like degeneracy sitting on top of the Planck results, but with a much broader range. Okay? So the green points are what you get from the temperature power spectrum alone, and then you add in the polarization, you get the red. And you see that what happens is that you add in the polarization, it clips off parts of this line-like degeneracy that don't fit very well with the BAO. And that's beautiful when you see things like that. You add in the polarization data, the consistency with the BAO improves. So those are just fits to the line-like degeneracy. The overlap region basically tells you the value of H. Okay, so that's why if you combine WMAP with the BAO, you will get the same result as Planck for H with a comparable error. Okay, so the low value of H naught is a lambda CDM result that from the CMB that's not sensitive to which experiment you're looking at if you've got the BAO. Okay, so it's not a particularly Planck result. Okay, so it's very difficult to make it go away. The position of that line depends on the value of the sound horizon, and to emphasize this point, in the paper with Stephen Grattan, we gave you the acoustic scale parameter, theta star, for lots of different likelihoods, temperature, polarization only, TE only, combinations, and so on. Sigma is a parameter combination that's a good proxy to theta star, so simple parameter combination. And then omega m h cubed is an even simpler proxy to the acoustic scale. That theta star is determined to 0.05 precision from Planck, and it's just completely consistent. Okay. So I can't see that there's any scope for changing the CMB results. Okay, so, I lost a slide. It doesn't matter. So, my conclusion from this is that if your data, disagrees with Planck, whatever data it might be, H norm, large-scale structure, weak gravitational lensing, then either you're wrong or there's new physics. Okay? I don't think you can break Planck. Okay, so what kind of new physics might it be? This shows a reconstruction of H of Z that's conditioned to fit the BAO measurements from BOSS using the Pantheon supernova sample with the Planck constraint on the sound horizon, and you miss the shoes. You get and so there's no physics in this, right? You can't evade this problem by having interactions between dark matter and dark energy or anything like that, because it's just constrained. It's constraining H of Z enough to to give you a reconstruction. And so that's shown here, where and it doesn't matter what sound horizon constraint you use, you get the same result either from WMAP or from Planck. This reconstruction will give you a low value of H naught that's consistent with the Planck results, but discordant with the Shoes result. So I think this is generally accepted now, that if you're going to resolve this problem, then it involves changing the sound horizon, or maybe something more exotic, like the string gravity we heard about this morning. Okay, so now I'll give you, a summary of why I'm confused about this problem and why I'm nervous about giving this talk. And I've discussed this with Adam, so it won't be new to him. So I want to point out some problems with the distance anchors. We have two accurate geometric distance moduli for the Large Magellanic Cloud from detached eclipsing binaries, and for NGC 4258 from the Mason analysis. And so in this little test, I use the Cepheids as in the Shoes papers to go from one galaxy to the other. So using the Cepheids as an intermediary. And this shows you Cepheid period luminosity relations for the LMC, and then matched to NGC 4258. So the LMC are the blue points, and NGC 4258 the red points. And so then what you get is that the difference in distance moduli from the Cepheids differs from the difference in the distance moduli from the geometric measurements by 0.177 magnitudes. And that's a 3.5 sigma result, which translates to a change in the Hubble constant of 5.7 kilometers per second per megaparsec. Okay? Now, that ignored any metallicity dependence of the period luminosity relation. And so if we take some representative value, like that 0.14 plus or minus 0.06, which is what you get using the full set of Cepheid data from Shoes, then that can change this delta mu by 0.055. So you can reduce that 3.5 sigma discrepancy to maybe 2.5 sigma. But it's still a tension, and that's at the very basic level of the distance anchors. Okay? So this plot here shows you the normalization of the period luminosity relation for the LMC, so the red point is that 0.177, where that 1.177 comes from, without including metallicity variations. The blue is shifting it by 0.055. That's the NGC 4258 megamaser distance. Then the next point is Milky Way parallax measurements, where I get exactly the same results as Adam using the parallax measurements, and Andromeda from detached eclipsing binaries. So that's the status of the distance anchors, and it's not altogether brilliant. Okay, and I'm particularly worried about the inconsistencies of the top two. If we just took this at face value, then you'd say that if there's a problem, it's the megamaser distance that's wrong. The geometric distance to the megamaser may not be right. On the metallicity dependence, I would worry that the 3.5 sigma tension, ignoring metallicity dependence, is clearly bad news. I mean, we're only talking about 4.03 sigma tension, 4 sigma tension to begin with. If the problem with this is that it means that we need to know what that metallicity dependence is. And so you're now sensitive in this analysis to a small number of low metallicity Cepheids in the supernova host galaxy sample. Okay? So I regard that as problematic. Okay, now what happens, how does this translate to H0? So here are some solutions that I got, which Adam will disagree with. This is a controversies meeting. So let's look at this. Okay, I'll give my point of view. Adam, I'm sure, will give his point of view. So this is using the NGC 4258 megamaser distance and the Schu's Cepheid photometry. And there are 3 solutions. The first thing that bothers me, and has always bothered me with the Schu's data, is if I fit with NGC 4258, I get that B parameter is the slope of the period luminosity relation, and I get minus 3.07 plus minus 0.04. And for galaxies like the LMC and Andromeda, where we have loads of data, you get slopes of minus 3.3. So that's off, okay? And as a CMB person, if I'm going to use this as as a standard, I worry if it's discrepant with local measurements. Okay? So I worry, why is that slope as shallow as that? And it's statistically a very significant result. So I impose a slope prior, okay, of minus 3.3, which is the local slope, and I get that solution. So H0 70 plus or minus 2. Then we switch to the LMC and we see that we're getting systematically higher values. Okay? Now that's because of that tension in the distance anchors. Right? The geometrical distances are not consistent with each other. Okay, so you get higher values. So if I put no slope prior, you see that the slope has now changed from minus 3.07 to minus 3.2, and that's because we've added in the LMC, which has a nicely determined slope of minus 3.3, so it's pulling the slope of the period luminosity relation to make it steeper. And then the H0 is 76.3 plus or minus 2.5. Okay, maybe that's the right answer. Okay, and it's important, that if that were the right answer, then it would impact on all of the theoretical explanations that we heard about this morning, which are struggling to get above 71. So if I put in the slope prior, it'll it takes H naught down. Okay, whoops, it takes H naught down to 74.7. Okay, and I don't know which of these is correct. Okay, so my point of view is I don't know which of these is right. Maybe this tension between the distance axes is just a statistical fluctuation, that they differ by 2.5 sigma, and there's a metallicity dependence, and so on. And so the right thing to do is to average them, which is what Adam does. Maybe that's correct. But also, it might be that there's a problem. Okay, and I don't know. So I'm still, I don't agree with the menu approach because I still think there's scope for problems with this measurement. Now, what could you do? You could. There are ways of doing this. We've got to get a better handle on the metallicity variation, and we've got to resolve this problem of the shallow slopes. Okay, and I'd like to see resolutions of those problems, which we can do getting more data. So I'm left, you can't bend the CMB. We've already heard that physics, introducing new physics, is tricky. It's not natural. It doesn't work brilliantly well. And I think that there are still issues with the data that really bother me, and we should focus on. Put more effort into it. So I think I'll stop here. There's more that I could say on holy cow and so on, but I'll just stop if it comes up. We can discuss it further.
Okay, so now it's up to me as the theorist in residence to reconcile or find a solution, which I hope is not too controversial for this conference. So this is called the end-to-end test. The H-naught gain, I call it the end-to-end test, as Adam mentioned, basically because we are basically for the first time able to measure what we believe is the same quantity within our favorite model, but in one case we are measuring it at the very beginning of the universe, at the CMB, and it relies on physics in the early universe, which we believe, and we've solved the founding agency, that is simple, is linear physics, extremely well understood, with something that we measure here and now, and there's the entire universe in between. And given the size of the error bar that we have, it's basically like threading a needle from the other side of the universe. And we're almost there, because we're discussing about a few percent, but not given the error bars. So first question as a theorist I would ask is there a problem? And so first of all, you want to be quantitative, and I'm sure you have seen this kind of plot many times already. So this is from Jose Luis Bernal. This is the fence. I just stole one of his plots. And what we have here is that the model up there, up there are relying on early time physics, but are cosmological model dependent, and the error bars, the measurement down here are relying on late time physics, and they have minimal dependence on the cosmological model. In the time delay, there is some dependence on the cosmological model, is not much, but here there's no dependence on the cosmological model. And there are several versions of this summary plot, and the other version that you've seen come from the summary of a workshop in California in July. And the summary is that given the reported values, the tension is between 4 and 6 sigmas. And our working hypothesis here is there is an early versus late discrepancy, in the sense that the measurements that are on the low end rely on early time physics, and the measurement that are on the high end is late time. However, I call this a working hypothesis because we haven't tried all the possible, early and late time measurement and see that they always are in these two camps. So this is like a trend, and there should be other late versus early versus late measurement that should also comply to this if there is a late versus early problem. And there is, for example, a poster by Michele Moresco that will present one other route. Although all the other tests that we have, the error bars are not small enough yet to weigh into this. So this working hypothesis, early versus late, it's interesting. It relies on the fact that we can do the distance ladder, the cosmic distance ladder two-way. The traditional way of doing the cosmic distance ladder was to start here and now, and then measure distances in the cosmic distance ladder farther and farther away via CFAs and then supernovae. But the fact that the BAO measurement has achieved the precision that it has achieved, error bars of 1% at around ratio 6. And the fact that the interpretation of the BAO signal is calibrated on the cosmic metric background, the sound horizon at radiation drag, means that now you can do the cosmic distance ladder the other way. And there's not much wiggle room in the middle. There is some wiggle room, but there's not much wiggle room. So where is the problem? We find that one distance ladder doing with one anchor, when the other distance ladder doing the other way with the other anchor, don't quite agree with each other. So the first question to ask, is it in any specific data set, if we keep the lambda CDR model? So let's talk about the early part of the problem. For a while, some people put the blame on Planck. The H0 determination from the early time doesn't budge if you take Planck or CMB data completely out of the question. So for a while, people who dropped Planck had to use a combination on WMAP, ACT, or SPT. But this summer, there was this paper by Schallenberg and collaborators where they took the CMB completely out, and they just used big bang nucleosynthesis, early light element disabundance, and baryon acoustic oscillation, and then still found the same tension. Now, if you want to go a little bit behind the scene, first, this says this is not in the CMB data, because there's no CMB data there. Of course, there is the assumption of standard early time physics, so the way to compute the sound horizon or radiation drag is the standard. Now, we can go a little bit behind the scene and say, but in this paper, in order to be able to give me that nice red contour there, they had to use the Lyman alpha BAO and the Galaxy BAO. And we know that Lyman alpha BAO and the Galaxy BAO, for a while, they were not really agreeing with each other. Now they agree much better with the latest data release. They use the later data release. They say, well, if you worry about this, no problem. Throw away the Lyman alpha BAO. but put in there instead a prior and omega matter that comes just from the supernovae, because the shape of the supernova luminosity distance with respect to the redshift depends on omega matter. In a lambda CDM, it gives you omega matter, and it gives you omega matter with that error bar that is plotted as two purple lines vertical. So you can throw away the Lyman alpha BAO if you don't like them, and the summary is still the same.
So what are the red, blue, and
so the blue are the BAO from the galaxies, the green are the BAO from the Lyman alpha, the red is the combination, the violet is Planck, and the yellow is choose, determination. And the difference between left and right is whether an effective is left free or whether it's fixed to the standard value. So, again, where is the problem? Is it in any specific data set? All low-Rashi determination except one, which we heard about this morning, hovers above 70. So, when you are in this situation, I'll suggest to invoke Bacchus. No, not this one. It's another technique which was proposed by, again, Jose Luis Bernal and John Peacock a year ago. So the idea is the following. For my approach, this allows an unknown shift as a systematic error in each measurement. The technique is more, it's more general than that. You can also say that you don't know the error bars, and then you can also allow the error bar to scale. But for this case, also because the answer is analytic and I can do it very quickly, I allow an unknown shift in each measurement, and then marginalize over this unknown shift as a meta-parameter, and see where that leads you. So in a toy model like this, if you have 4 Gaussian measurements and you want to combine them, this is a conservative way that will tell you what the combined distribution is, that take into account, extends the wings to take into account that there may be unknown systematic shifts. And so if I do that, then it's a little bit of a busy plot, but I can do that combining shoes, and then Holy Cow, and then surface brightening fluctuation, masers, or I can add the tip of the red giant branch with or without the correction for extinction. So what is this saying? This combination basically says, well, the central value doesn't budge much, but I allow extra wings to actually say what in a standard combination will be 5 sigma, now is not 5 sigma anymore, because I allow for this unknown shape. And so what I get is that this combination is 2.6 or 2.8 sigma away from an H value of 68 or 67.4. You can read the answers. So it's a 99% or 99.5% dependent. So, and this is what happened if you add this. Okay. So, no talk is complete without a Brexit joke, so here's one. I want to have you a meaning of what these percentages mean, because we know 1 sigma, 2 sigma, we know that 5 sigma is the golden level, and then beyond 5 sigma we claim discovery or something. But this is, so both the 5 sigma threshold and this Bacchus combination technique were motivated by something like this. So I took this from Nature. Nature is running, or was running, a series of small opinion articles about p-values and statistics and things like that, which is extremely important, not for physics. In physics, we do things actually quite well. But for other fields that were coming out with discoveries. So the history of science is littered by discoveries that turned out not to be discoveries, in part because the statistic was not done correctly and there were systematic errors. But doing both would probably be one too many, because there are two techniques that are thought actually to protect you for the same thing. So let's keep going back to the question. So now, where is the problem? If not in the data, then maybe it's in the model. Now, this is a big statement, which reminds me of this. And now we've heard of the guillotine and the French Revolution, and this one ended up with the Inquisition, so I don't know what's better, but you know, if we start attaching the model, then things are at stake. So where is the problem? If not in the data, then in the model. Early time measurement assume lambda CDM, and effectively this yield the length of the standard ruler, and then we rely everything on the length of the standard ruler. And as we've heard this morning, if you keep this function history as a lambda CDM between today and the last scattering surface, you can reconvert the H0 problem into a sound horizon problem. While low redshift measurement tend to do much less assumption about cosmology. So here it's another way to present this tension. There is h, little h on the bottom axis, and this is the sound horizon at radiation drag. And then we have the constraint from shoes, the constraint from VAO plus supernovae, and the constraint from the CMB, if we assume that this is the termination of the sound horizon. Okay, so we heard already this morning, you have two ways to solve this. You have the CMB gives you a triangle. You can make the triangle smaller, or make the triangle in a different position. So you can ask, could the solution be imposter combination? And we've heard a very creative attempt this morning by Tesmon here about modifying gravity, putting some screening, and then in this way basically altering the way we interpret the supernovae data. Now this, however, will not solve the time delay, because, or at least you have to invent another mechanism that also will change the time delay in the same way. You can increase the freedom of HOC and low redshift, but there are some examples, but the price is high, and you end up adding many extra degrees of freedom, and at that point you ask yourself, am I adding epicycles? And I'll go back to the epicycle in a bit. So it's very hard to change the sound horizon by 7%, which is what is needed to solve this tension. One has to tinker with omega barium, which is hard, with omega matter h squared, 20%. And you have to do that without changing the matter radiation equality scale, which we see in the CMB. Or you can say, well, I want to instead mess around not with the sound horizon radiation drag that the CMB gives you, but the one that is actually imprinted in the larger scale structure. I mean, something may be going on in there, in that process, but it's hard to mess around with that at the 7% level. So, let me show you some of my slides from a couple of years ago. I was saying that the anchoring is uncomfortable. We are a little bit in this situation, up, up, now, down a little. And I was saying that, maybe we are not quite at this stage yet, but now we've seen that maybe now we are at this stage. Okay.
There's a code of conduct.
It's not a safe space.
So, before we come with solutions, we have seen the constraint from throwing away the CMB. This solution bypass that constraint. That constraint add number of effective neutrinos and in the calculation of the sound horizon, but you can be smarter than that or do something a little bit more elaborated than that and evade that constraint. So pre-recombination solution. So let me say the following thing first. It's that you start to modify the model right where we love the model most. because we have been telling the funding agency that simple physics extremely well understood. That's why we should look at the cosmic microwave background and constrain the model this way. And now we are tinkering with the model right there. In some sense, this is also a good thing because they tend to affect the universe in an unobservable that has been probably the most successful so far and that is extremely sensitive. So, the goal is to decrease the sound horizon by 7%, or the effective sound horizon by 7%, without breaking havoc on the damping tail, on the polarization, and on everything else. And we have heard that this is a very tall order to do that. So we have seen for the talk this morning that in order to be successful at doing this, you want to put all your fish somewhere here, because this is where the sound horizon comes, and this is where the damping scale comes. You don't want to tinker around with the damping scale, you want to tinker around with the sound horizon, but the most of the sensitivity of this is exactly what most of the sensitivity of this other quantity is. So you have to design model that tinker around with things here. And that's why it's difficult to get to that 7%, because you don't have the maximum sensitivity. And an example is the changing an effective changes everything here. And that's why it's now down. So this reminds me a little bit of fine-tuning, because you have to fine-tune things, so you just modify it. So models, early dark energy affect the damping tail, so we can look for signature for that in forthcoming data, and Joe Dantley this morning gave us an example of this. You can change initial condition, you can think about adding extra component, but then you also have to add extra interactions in order to hide the effect of this extra component in that damping tail. You can think about energy injection, but again it needs to be very localized. We've heard the high temperature recombination. Or you can try to change H of Z at early time in a sort of well-designed way, but you would have to find a physical motivation for actually doing that. The nice thing is that these are not all equivalent for observable that we are going to have in our hand very soon. And so in this sense, these are very predictive changes. So before I finish, I want to try to convince you that we can go beyond the H0. This is not just an H0 problem. If you think in terms of early versus late, or if you think in terms of tinkering with the lambda CDM model, it's not just an H0 problem. It's an omega matter problem too, right? And this is another way to restate the same problem in terms of omega matter. Now it is what the CMB tell you, what H tells you, and what BAO plus supernova tells you on omega matter. So we also have a problem in omega matter, but the error bars here are a little bit bigger than in H0, and that's why the main problem is in H0. And what's the age of the universe anyway? Because if we have this problem, we also should also see this problem in the age of the universe. So we, in my group, we look at it early on this year, and we combine constraints on H0, which we all know and love, a couple of measurements from the age of the universe, one coming from a combination of low metallicity stars, and the other one coming from the age of 18 globular clusters. There is slightly different colors. These lines here are the constant of omega matter in this plane, and this is a constant equation of state of dark energy, and this is what Planck loves. So anyway, so how old is the universe anyway? It's also linked to this question, because this is where we are in the age of the universe versus H0 in a lambda CDM model. So let me conclude about theoretical solution. Whatever theoretical solution we can come up with, assuming that we decided that is not a problem in the data, and we've seen that the last few wrinkle needs to be ironed out, should improve or not worsen other tension. And it should not destroy whatever works very well in the lambda CDM model as we have it. We should quantify improvement versus predictability of the model, and this is the degrees of freedom consideration that I say. It's nice to ask yourself, am I taking a model-dependent or a model-independent approach? Because if we are testing the model itself, we can't use the model to actually test the model itself. It would be a circular argument. And so there's some food for thought there. And we need to ask ourselves, at what point are we adding epicycles? So here is two reproduction of originals of epicycles. One is the illustration by Cassini, and this is in an Aristotelian system where the Earth is in the center, and the epicycle were added just to follow where the planets go. On the other side here, the Copernican model of the solar system also had epicycles. But these were of a completely different nature in the sense that those epicycles were the clue for Kepler to actually say, no, the orbits are not circular, they are elliptical. And then everything, converged to the right model. So my question for the discussion here is, all this effort that we are doing is basically to tell us where we should add epicycles and where we should not add epicycle and what type of epicycle we should add. But the question we should add is, are we here, which we need to throw the model completely out of the way because we are adding epicycle because we are in the wrong track? Or is it here and the epicycle actually give us a hint on what the small correction we need to add to the model may be? And before I conclude, I was a graduate student where this was all lambda and the supernovae and the accelerating universe came up. And I remember there were a lot of parallelism between the discussion we are having here today and that discussion back then. And one of the problems I remember was about inflation, right? Because you wanted a low omega matter if you don't have lambda. But inflation will not give you a low omega matter. Or, you can try to squeeze it to make sure that maybe inflation will give you a low omega matter. It sounds to me simple. So I'll stop here.
So as we start our discussion amongst the panel first, I think what we all can see is that this is a very interesting problem, and what is at stake is new physics. And if we can establish that there actually is a significant discrepancy, then we're going to learn something about the universe. And I think that's why so many of us are in the room working on this problem now. I wanted to bring a thread that I think was common amongst the various panel speakers this afternoon, having to do with, first, Alicia, you talked about a new analysis where you increase the systematics, where there might be unchecked systematics and you can increase it. I think George raised the question that there are very serious differences amongst the anchors, and I'll give you your time. And that we need to be careful to understand where there are systematics in the anchors. And Adam talked about a number of different H0 values. Alicia showed a different version, but it comes from Adam's analysis where you put a lot of different measurements up, which may or may not be independent and in some sense combine them all together. I wanted to comment that the systematics, so the anchors, if the distances to the anchors change, then H0 changes. The different methods will float up and down with the anchor distances. That is a systematic. And so simply broadening the tails of the distribution tells you nothing about that. So there's a real danger in saying, okay, there's a great agreement amongst various H0 values because the anchors could change. Okay, I'll get to you, Adam. If you look at this plot, and maybe Adam, you want to show your version, you're welcome to do that. I think we have to be slightly careful about what goes up there. It looks like a lot of values there. Adam had even more, maybe 20 different H0 values. But for example, with MIRAs, you could calibrate with the Large Magellanic Cloud, you could calibrate with NGC 4258, you could average them all together, and then you have 3 different values that go up there. It's based on one distance to a galaxy where there's a Myra distance. It has one supernova that is calibrating, sets the basis for that calibration. It isn't quite fair to put it into a long table as if there has equal or almost equal weight. You had an error of 1.2.
It has the weight from one single supernova. That's just the weight it has. I mean, that's
Yeah, but a very small error that you quoted of 1.2. It's 3.9. That's what was in the meeting at Santa Barbara this summer, but it's coming down.
5%. That's what you get for one supernova.
Oh, okay, okay. You know, the SBF measurements were presented at the conference. It was new data. You had 3 values up there for SBF and so on. I don't want to belabor the point, but we need to be careful. And then someone comes along and says, well, you broadened the tails. But as George has showed us, there are significant differences in the anchors that I think we need to understand. So I think Adam probably wants to say something about why we should not believe George.
So the broadening of the tail comes because each measurement, it's allowed to shift. So each central value of the measurement is allowed to float. But then these meta parameters get marginalized over because you don't know which data set has which shift.
Right. But the point is, small number of anchors, there could be large shifts in the diagram.
Yeah.
And they'll all be affected.
All right, so if you haven't had your data reanalyzed by George, then you're just not in the club. So I'm in the club. I think there are many other people in the club. So this is a hobby of George's, and he's very good at it. But I do wanted to point out some of the fun games he played with. One of the ways that he shifted the Hubble constant a fair bit is by setting priors on parameters, nuisance parameters, slope, metallicity, that are 3 and 4 sigma away from the nominal fit. And so if you move those 3 or 4 sigma away, you move away from the central value 3 or 4 sigma. So you're just trading tensions. I don't think it's, my view, legitimate. Otherwise I would go up to George's data set and I would set lensing A sub L 3 sigma higher than it is, and I could get the Hubble constant that I wanted. So that's one point that I wanted to make there. Well, I'll get to that. So, thank you, Brad, for reminding me. So, you know, in terms of that, I agree exactly with what Wendy said. See, I said I would fit that in there at some point. I agree exactly with what Wendy said. That we have to be careful. You change one, you change the large dimensional anticloud and it ripples through everything else. So what I liked about this approach is you get your peremptory challenge. So if you don't trust an anchor, if George isn't sure about 4258, then this is your value. And we were careful with TRGB to include your value without changing anything about it. And so this is exactly your value with the other things, excluding all the other supernova distance ladders. So, you know, going back to all of these, right, that's saying I'm going to take your value exactly, and I'm going to throw out everything else. That's, you know, that's pretty centric towards CCHP, I would say, to take just your value and throw away everything else. But then we include these things that are unrelated to your measurement. And so that's how we arrive at a value like this. So this is why I'm saying I don't see a way out short of throwing away 3, 4, or 5 things. And I think if we throw away lots of data, we will return to ignorance. And, you know, it's almost a tautology. So, you know, we're just going to have to deal with, we have disparate data. And I agree with you that we have to be very careful because there's covariance to make your combinations. These individual values are not, you cannot say that they are correlated with each other, of course. It just allows you to choose your favorite combination. And I think this would be your favorite combination, but it is still 4 sigma away from blank. I mean, it just,
But you've averaged in your mean analysis of our...
No, this is your value just as it was, untouched. Your 69.8, just as it is.
Yeah.
The only value taken from this entire group of supernova distance ladders, and then taking one of these, this, and this. It's holy cow and masers.
Could be the next slide, but
Yeah.
this was 69.8.
This 69.8 is averaged in. It's the only thing from category 1. The only supernova distance ladder I've taken here is your CCHP value. So it can't do better than that.
Okay, but I'm asking what gave you 72.5?
72.5 is, sorry, the average of 69.8, that plus one of these, plus this, plus this. That's how you get to 72.5. So it's just the fact that there are other players in this field that are, and so.
Okay, but you know, you're putting in things, you've got a real collection, a disparate collection.
Well, you know, you could choose your,
Unpublished data, I mean, it's,
well, you know, you get your one periphery challenge, but you can only challenge, you can't throw away the whole jury. Right?
yeah.
So, all right.
Yeah, I was, sorry, I really was worried about this session, okay? And,
We're just getting started, George.
and you know, I mean, I don't believe anything that anybody does unless I do it myself.
You are the
You know, my distrust. My distrust of my fellow scientists is because, you know, I had a very unhappy childhood, so please don't take it personally. You know, everything that you said could be right, okay? It could be a fluke that there's a tension, sorry, it could be a fluke that there's a tension between the distance anchors. My worry is that it may be telling us something. And what I was trying to say was that I see three things that I would like to see more work on, and we can do more work on. I think both the distance anchors, the LMC and the MESA, they should be looked at again more carefully to see whether there's something, you know, something wrong with the geometric
But George, just to be
distances.
clear, with the metallicity that we know about in CEPI, it's only a 2.1 sigma difference. I understand they're different,
Well,
but it's not, I mean, there's a bigger difference
Okay,
between
but
high L and low L than there is between those two.
Okay, so I still think that it's worthwhile looking more carefully at the geometric distance anchors. They're fundamental to the whole distance scale, so it's worth putting some more effort in. We'll get more information with Gaia as Gaia improves. So this is a problem that we can do more work on. The point about metallicity dependence, it's been a problem in this field for decades.
For years, yeah.
Okay. My point was that it means that the solutions are reliant on a relatively small number of low metallicity settings in your sample, and that's a problem that we can do something about. We can get more data in the outer parts of galaxies and pin it down because it is important. Okay? So we need to do more work on that. Then my third point is, and this really does worry me, okay, is I would like to understand why the slopes of period luminosity relation in the Hughes daisy is so shallow. Okay, and I'd like to get an understanding. So it may be right. But what I was trying to say was that I think that there's scope to look at these problems and sort them out, and it's important.
Agreed. Okay, I'm going to open it up now to the audience. We'll have questions for the panel. Mark.
Microphone?
George, Adam, you spoke about the necessity to throw out all galaxies with redshifts less than 3,000 kilometers a second from us. Are you still doing that?
Yeah, so we set the Hubble flow to start at redshift 0.0 at 7,000 kilometers per second. That's a historical convention that, for years people would say, maybe there is a little bubble nearby and that you would have a coherent flow. Now we think I think you're thinking this doesn't exist anymore, so we could go lower.
Yeah.
And it doesn't change things very much, but, I think that you have no idea how many people write papers saying we live in a giant void. And our only recourse sometimes is to just go further and further out just to make them stop writing papers.
Well,
It doesn't work. It doesn't work.
you showed a sample of 19 or 20 brand new
Oh, for those.
For those.
Those we never use the redshifts. Those are just co-located supernova and Cepheid. And so that's as far out as we can go with Cepheids. that distance, 0.01. It's a distance.
Why don't you, are you using my peculiar velocities?
Yeah, so we don't, right, you're saying we don't make a Hubble diagram with those objects because they're so nearby, the peculiar velocity terms would be pretty large.
Not if you put in a correction.
Yeah.
Well, the plot that Barry showed this
Corrected
morning,
flow
yeah,
is
the two,
You should-
down to very
right.
small scale.
Well, you should, the people who are doing gravitational lensing should listen to what Mark is saying because they have objects, or their one object is at 40 megaparsecs, and they've been arguing about what the peculiar velocity is, trying to get a Hubble constant.
You know, the trouble is, it's my fault for not making this peculiar velocity field more available.
Yeah.
If somebody wants to work with me, it's now in ancient Fortran. If anybody's still, Fortran's fine,
can't be
but,
converted.
you know, we can fix it.
Other questions? Yeah, that would.
I just wanted to hear what George had to tell us about Holy Cow. Because I knew you weren't worried enough.
Okay. There was nothing very profound. Okay. We had a nice talk this morning. One of the things that's worried me with lenses is the constraints on external convergence. Okay? And the way that that correction is done in this, you've got to, it's completely degenerate with H0, so you've got to get that right. So that worries me. But you've seen the constraints on H0 from the gravitational wave system. If you put a constraint in VLBI on the inclination angle, and that lops off the high H0, the posterior lops off, just falls off and doesn't allow high H0 values. So the simple thing that you can do is do a hyperparameter analysis with that constraint in, and the 6 Holy Cow lenses, and that gives you H0 of 70 plus or minus 2. So it downweights the high Holy Cow constraints. So, I mean, I don't believe it. Okay, I don't believe that gravitational wave posterior. But the point about that is that if you take it at face value, you get a low value of H0. Okay, and that's not an early late time thing. It's a data question. What data do you believe? What data is reliable? That's
Question over here.
Sorry, I don't.
Wait for the microphone.
So can you explain again why the Holy Cow result will drop to 70 because of? Can you explain again? What's your argument for that? For the
it's simply the Holy Cow has a spread.
Yes.
Okay, and there's one system that is peaking at around 80, which has quite a small error, and that gets down weighted by the gravitational wave neutron star merger event, provided that you believe the model with the constraint, the VLBI constraint on the inclination. That's.
One last question. Oh, sorry, there you two. Go ahead.
Hi, I just want to ask some new way of measuring, for example, new way of measuring H-star. So I heard a talk about using the neutron star merger and standard siren. So I think there's also a paper about using kilonova to do that, because that's also similar to standard siren. It's like neutron star merger. So I don't know if here people thought about it more, and what's the perspective in measuring H-star to like higher Z? Thanks.
Dan, are you here? Do you want to field that one?
Sure. Right. I mean, I think that's using kiloNova as standard candles in the same way as type lights.
But can you combine them with
So in all this, and I'm a little, I mean, to this point of the strong lenses, so the way I think of standard science is just its own independent measurement. You can combine it with, whatever you like. If you add modeling, okay, you get improved constraint, but with potential systematics. But you could just as well say, I'm going to use Planck as my prior and analyze the strong lensing, and then you'll also get a OH0. So
maybe I say it correctly. What I'm saying is like using a kiloNova as a standard candle, like using optical.
Yeah, so you could do that, and I guess you could probably, fix the standard candleness by using the gravitational wave observations. But fundamentally, now you're treating that. Do you understand a kiloNova emission as well as you understand a type 1A? And that's going to be somewhere to get to that confidence.
Okay, Gary, you had your hand up, and then we're going to end the session.
I just have a question, mostly, I guess, for CFE and theory sides of this. If ACT-TE comes up with something that disagrees with Planck, where does that point us? Is that pointing you towards a certain idea about something experimental, or is that pointing you towards a certain idea about a particular early universe change?
It would depend on the multiple. So, yes, it would depend on the multiple range. Okay, if new measurements that are outside the multiple range program by Planck pull you towards, a different model, then if those measurements are right, that's the real world. Okay. If they're discrepant with Planck over the same multiple range, then we have a real problem. That's a real tension.
Okay, before we begin, I just want to make one final comment, which is I think despite all the controversy, we hear a lot about it, there's been considerable progress over the last decade, and I think the fact that we used to argue over H0 at a level of a factor of 2, and we're now vehemently arguing about agreement at the 10% level that's coming from measurements of the cosmic microwave background and Cepheids and red giants and so on, is really quite remarkable. We don't take the time often enough to appreciate that we've learned something. And the possibility of learning new physics if we can get our systematics under control, I think is very real. So let's stop here and thank everyone.
I think the data public should make you feel better about these two counts, because now the data are public. So anybody